What if the next global superpower isn't defined by military might, but by a breakthrough in quantum computing, a silent shift where the architectural integrity of a nation's secrets becomes more significant than the thickness of its armor or the range of its ballistic missiles? Inside the subterranean levels of the Maryland facility, the air is scrubbed of particulates and maintained at a precise humidity to prevent the slightest static discharge, creating an atmosphere of unnatural stillness that mirrors the cryogenic heart of the machine at the center of the room. Dr. Elias Thorne stood before the dilution refrigerator, a towering assembly of gold-plated copper plates and stainless steel supports that resembled a high-tech chandelier, or perhaps a temple to a god of absolute zero. Within this vessel, the temperature was being driven down to 15 millikelvin, a fraction of a degree above the theoretical limit of the universe, where the thermal noise of the macroscopic world finally yields to the strange, probabilistic dances of the subatomic. The hum of the pulse tube precoolers was a rhythmic, industrial heartbeat, the only sound in a space where human breath felt like a violent intrusion of entropy. The race for quantum supremacy, a term that had transitioned from a theoretical provocation in a 1982 Feynman lecture to a tangible geopolitical pivot point, was no longer about the mere speed of calculation, but about the fundamental nature of problem-solving itself. Unlike the classical bits of Elias's youth, discrete, binary pulses of high or low voltage that define the digital age, the qubits suspended in the superconducting circuits below were entities of precarious superposition, existing in a state of both and neither until the moment of measurement. This was the computational advantage that Google had first glimpsed in 2019 with its Sycamore processor, a device that performed a specific sampling task in seconds that would have occupied the world's most powerful supercomputers for millennia. Since then, the threshold of supremacy had moved from laboratory curiosity to a functional reality. As the gate fidelities improved and the error correction codes, like the surface code, began to stitch together fragile logical qubits from hundreds of noisy physical ones. Elias watched the telemetry on his monitors, observing the coherence times, the brief window where the quantum state remains uncorrupted by the environment, stretching from microseconds into milliseconds, a duration that felt like an eternity in the realm of nanosecond gate operations. The implications of this leap were not merely mathematical. They represented a phased transition in human capability, where the simulation of molecular dynamics for room temperature superconductors or the optimization of global logistics could be solved with the same ease as a grade school addition problem. Yet beneath the promise of material revolution lay the darker reality of the cryptographic collapse, a looming event often referred to as Q-Day, when the mathematical foundations of modern civilization would be rendered transparent. The RSA and elliptic-curve cryptography that secured every financial transaction, every diplomatic cable, and every command and control system relied on the inability of classical hardware to factor large integers or solve discrete logarithms within a human lifetime. Shor's algorithm, a mathematical ghost that had haunted the intelligence community since the mid-90s, was the specter that turned these quantum chandeliers into weapons of mass decryption. As the qubit count climbed, the golden chandelier before Elias was slowly becoming a skeleton key for the digital world, a tool that could unmake the privacy of billions. He felt a profound sense of weight in the silence, a realization that they were not merely building a faster computer, but were engineering a device that could effectively erase the past 30 years of digital history by unlocking the archived data of every nation-state on Earth. This was the Silent War, a conflict played out in the whispers of wave-function collapse and the infinitesimal shift of phase-shift gates, where the victor would hold a monopoly on the world's information before anyone else even realized the locks had been picked. The stillness of the lab was deceptive. It was the quiet of a fuse burning toward a cache of data that constituted the collective memory and security of the modern era. Elias adjusted his glasses, his eyes tracing the intricate cabling, thousands of coaxial lines carrying microwave pulses that whispered commands to the qubits, and he wondered if the world was truly prepared for the transparency that was about to be forced upon it. The transition from the classical to the quantum was a one-way bridge, and as the cooling cycles reached their target, the transition felt less like a triumph of engineering and more like a descent into a landscape where the old rules of power and secrecy no longer applied. Every secret ever told in the digital tongue was now on a countdown, waiting for the moment when the coherence remained stable long enough for the algorithm to run its course. It was a meditative, terrifying reality, a technological earthquake whose tremors were already being felt in the frantic, classified halls of power across the globe. In the shadowed, climate-controlled depths of the Utah data center, the hum of 4 exabytes of spinning magnetic platters and solid-state arrays creates a low-frequency thrum that resonates through the floorboards, a physical manifestation of a world's worth of encrypted secrets held in a state of suspended animation. This is the silent harvest, a practice known among intelligence circles as store now, decrypt later, where the encrypted streams of diplomatic cables, banking transactions, and private correspondences are intercepted from undersea fiber optic cables and vacuumed into massive silos, despite the fact that current classical supercomputers would require the remaining lifespan of the universe to crack their codes. For decades, the security of the global digital infrastructure has rested upon the elegant difficulty of the integer factorization problem and the discrete logarithm problem, mathematical trapdoors that are easy to fall through in one direction but nearly impossible to climb back out of without the secret key. Before we go deeper, if this calm pace feels good, consider subscribing so more chill science waits for you when you need it. When a person makes a purchase online or a general sends a command, their data is shielded by RSA 2048 or elliptic-curve cryptography. These systems derive security from the fact that finding the 2 enormous prime numbers that multiply to form a specific 617-digit product is a task of such staggering complexity that it defies the brute force of every transistor on Earth. Elias, walking through the rows of blinking blue LEDs that signaled the constant ingestion of this dark data, understood that this cathedral of secrets was built on a foundation of sand that was already beginning to shift under the influence of quantum mechanics. The vulnerability lay in the very nature of Shor's algorithm, which bypassed the step-by-step trial of classical logic by utilizing the principle of quantum interference to find the periodic nature of modular exponentiation. Essentially, it finds the heartbeat of a large number's mathematical structure. While a classical computer must check every possible factor one by one, a quantum processor of sufficient scale and coherence can manipulate the probability amplitudes of every potential answer simultaneously. The incorrect paths destructively interfere and vanish, while the correct factors emerge through constructive interference. This process, facilitated by the quantum Fourier transform, transforms a problem that scales exponentially with the size of the input into one that scales only polynomially. That distinction represents the difference between a lock that takes 1 trillion years to pick and one that pops open in a few minutes of quiet computation. As Elias contemplated the vast racks of stored data, he realized that the encryption Armageddon was not a future event but a retrospective catastrophe. Every piece of information sent over the internet today is already vulnerable to the future, a reality that renders current privacy an illusion maintained only by the temporary absence of a large-scale, fault-tolerant quantum computer. The physical reality of the qubits, the way they must be shielded from the cosmic rays and the thermal vibrations of the macroscopic world, was the only thing standing between the present and a state of total transparency. In that state, every bank account could be drained, every military secret exposed, and every private confession read by whoever first masters the stabilization of the quantum state. This latent threat creates a peculiar psychological tension, a sense of pre-post privacy, where the urgency of developing quantum-resistant defenses is balanced against the knowledge that the data already stolen and stored is likely lost forever to the prying eyes of tomorrow's silicon and gold processors. The mathematical elegance of the primes, once thought to be the eternal sentinels of the digital age, was being dismantled by the realization that the universe does not calculate in the binary certainties we once assumed were its fundamental language. Instead, the universe functions through the fluid, overlapping waves of quantum probability, and as our machines begin to speak that same language, the rigid walls of classical cryptography are becoming as porous as a net. Elias watched the data intake monitors, the cascading lines of green text representing millions of encrypted packets being saved for a day of reckoning that was no longer a theoretical if but a logistical when, and he felt the immense weight of a world that was effectively living in a glass house whose curtains had not yet been drawn. The silence of the server room was not the silence of peace, but the silence of an archive that was slowly, inevitably, becoming a library where every book would soon be open to whoever possessed the right kind of light to read them. This transition signifies a fundamental reorganization of the concept of a secret, moving away from the permanence of mathematical hardness toward a fleeting, temporal window of security that must be constantly renewed against the advancing tide of computational capability. The transition from the era of classical certainty to the era of quantum fluidity is the most profound shift in the history of information, and the silent humming of the Utah vaults was the sound of a world holding its breath, waiting for the first light of a quantum sun to reveal everything that had been hidden in the dark. Beyond the cold, sterile vaults of the American intelligence apparatus, the race for quantum supremacy manifests as a sprawling, multi-continental topography of shimmering optical tables and whispering dilution refrigerators, a geopolitical chess match where the pieces are individual ions and pulses of light. In the high-tech corridors of Hefei, China, the pursuit of dominance has taken a different physical form, utilizing the Zhejiang processor to achieve a demonstration of Gaussian-Boson sampling that far outstripped the capabilities of the world's most advanced classical supercomputers by factors of trillions. Unlike the superconducting loops of the American systems, which rely on the delicate flow of Cooper pairs through Josephson junctions, the Chinese approach often leverages the inherent stability of photons, particles of light that do not interact with their environment as easily as electrons, yet require immense precision to steer through intricate networks of beam splitters and mirrors. Before we go further, if you enjoy slow, quiet explanations, subscribing makes it easier to find chill science next time. Elias often found himself staring at satellite imagery of these international facilities, recognizing in the architectural footprints the same frantic, well-funded urgency that had characterized the nuclear race of the mid-20th century, though this conflict lacked the visible fallout and atmospheric testing of the previous era. The silent war was being fought over the mastery of the Hilbert space, that abstract mathematical territory where every possible state of a system exists in a shimmering veil of potentiality until it is collapsed by an observer's measurement. This competition is not merely a quest for faster computation, but a strategic grab for the ultimate asset of the 21st century, the ability to simulate the quantum world with perfect fidelity. A nation that achieves stable, large-scale quantum simulation first will not only be able to dismantle the cryptographic locks of its rivals, but will also possess the singular capability to design room-temperature superconductors that revolutionize energy grids, discover catalysts that sequester atmospheric carbon with unprecedented efficiency, and engineer molecular-scale medicines that render current pharmaceuticals as primitive as bloodletting. The ethical tightrope of this development is stretched thin between the promise of a post-scarcity society and the reality of a total technological hegemony, where the first mover might become an unassailable sovereign, holding a monopoly on both the world's secrets and its most advanced material science. In Europe, the focus has pivoted toward the creation of a quantum internet, a network where information is transmitted via entangled particles that ensure absolute privacy through the no-cloning theorem, a fundamental law of physics which dictates that it is impossible to create an identical copy of an unknown quantum state. This creates a fascinating paradox where the same technology used to break all classical locks is also the only thing capable of forging a truly unbreakable one, a defensive shield built into the very fabric of the vacuum. Elias contemplated the Mishas satellite, a lonely sentinel of Chinese engineering that had already demonstrated the distribution of entangled photon pairs over thousands of kilometers, effectively proving that the quantum landscape could be expanded from the micro scale of the lab to the macro scale of the planetary orbit. This global race is characterized by a strange duality. It is a collaborative scientific endeavor where papers are published in international journals, yet it is simultaneously shrouded in the highest levels of national security classification, with export controls on specialized lasers and cryogenic components becoming the new instruments of diplomacy. The stakes of this race are nothing less than the reordering of global power dynamics as the traditional metrics of influence, GDP, military personnel, and industrial output, are increasingly shadowed by a nation's qubit count and gate fidelity. As Elias monitored the transatlantic cable's traffic from his terminal, he felt the invisible friction of these competing ambitions, a tension rooted in the knowledge that once the quantum threshold is fully crossed, the world will be divided into those who can see through the digital walls and those who remain trapped behind them. This era of quantum competition represents a fundamental shift in how humanity relates to the physical world, moving from a period where we merely observed the laws of nature to one where we begin to program them at their most basic, probabilistic level. The silence of the laboratories around the world is the silence of a slow-motion explosion, a transformative event that is quietly rewriting the rules of what it means to be a global superpower in an age of information. The transition is inevitable, a geometric expansion of capability that threatens to leave entire nations vulnerable if they cannot adapt to the strange, non-linear logic of the quantum realm before the classical era finally, and permanently, recedes into the background. The task of fortification felt less like building a wall and more like rewriting the genetic code of an entire planetary ecosystem while it was still in motion, a reconfiguration of the logical bedrock upon which every digital interaction was predicated. Elias spent his nights submerged in the dense, multi-hundred-page standardization reports issued by the National Institute of Standards and Technology, tracing the evolution of the post-quantum cryptography project which had, after years of rigorous scrutiny, identified the mathematical structures capable of withstanding a quantum assault. The shift was fundamental, moving away from the number-theoretic hardness of integer factorization toward the geometric complexity of high-dimensional lattices, specifically the learning with errors, or LWE framework that underpinned algorithms like Crystal's Kyber. Unlike the smooth, predictable curves of elliptic-curve cryptography, these lattice-based systems functioned within a 1,000-dimensional vector space, where the security of a message was hidden within a shortest vector problem of such staggering dimensionality that even the parallel processing power of a fault-tolerant quantum computer could not efficiently find a solution. To visualize this was to imagine a crystalline structure of points extending into a mathematical infinity, where an adversary is given a point slightly offset by intentional noise and tasked with finding the nearest actual lattice point. It was a needle in a haystack where the haystack itself was an abstract, multidimensional labyrinth. Elias watched the simulations of these new protocols as they were stress-tested against the most advanced known quantum algorithms, observing how the noise injected into the LWE problems acted as a protective shroud, a mathematical entropy that refused to yield to the interference patterns of a quantum processor. Yet the theoretical security of these new lattices was only the first hurdle in a logistical marathon Elias often thought of as the Quantum Y2K, a global effort to migrate the world's data infrastructure before the first cryptanalytic scale quantum machine could be brought online. This migration was a monumental undertaking of invisible engineering, requiring the replacement of cryptographic primitives in everything from the firmware of oceanic fiber optic repeaters to the embedded microcontrollers in municipal water treatment plants and the secure enclaves of billions of smartphones. The challenge was compounded by the fact that these new quantum-resistant keys were significantly larger and more computationally intensive than their classical predecessors, threatening to choke the narrow bandwidth of legacy satellite links and slow the microsecond latency requirements of high-frequency trading floors. As Elias coordinated with international standards bodies, he felt the immense friction of a world trying to pivot its entire security paradigm. It was like attempting to replace the foundation of a skyscraper while the building continued to grow upward, floor by floor, into the clouds. There was a constant, low-grade dread that some vital, forgotten system, a legacy SCADA controller in a power grid or an ancient database in a national archive, would be overlooked, left vulnerable like a single unpatched window in a fortress. He often found himself contemplating the biological parallels, viewing the PQC transition as the development of a new digital immune system, one designed to recognize and neutralize a pathogen that didn't even fully exist yet in the wild. This proactive defense required a strange kind of temporal gymnastics, protecting the secrets of the present from the technology of the future, while simultaneously trying to salvage the secrets of the past that had already been intercepted and stored by adversarial entities. The atmosphere in the facility had shifted from the speculative excitement of the early quantum experiments to a weary, focused determination, as engineers worked to implement hybrid encryption schemes that layered the new lattice-based defenses over existing RSA protocols to ensure that even if the new math contained a hidden flaw, the old walls would still stand for a little while longer. Elias monitored the telemetry from a testbed in northern Europe, where a segment of the financial grid was being migrated to a quantum-safe, trustless architecture, observing the slight increase in packet overhead and the subtle jitter in handshake timings that signaled the birth of a new era of digital trust. It was a meditative, painstaking process, the slow work of future-proofing a civilization that had grown perilously dependent on the permanence of mathematical shadows that were now being burned away by the rising sun of quantum supremacy. The silence of the lab was no longer the silence of the vacuum, but the silence of a construction site where the hammers were made of logic and the bricks were made of high-dimensional geometry. Elias adjusted his monitor, the glow reflecting in his tired eyes as he realized that the success of this transition would never be celebrated with a headline. Its only reward would be the continued, uneventful functioning of a world that would never know how close it had come to a total collapse of privacy. The transition was a silent, monumental shift in the architecture of the human record, a testament to the capacity for foresight in an age characterized by its obsession with the immediate. As the algorithms were finalized and the first true quantum-safe packets began to traverse the global backbone, Elias felt a fleeting sense of equilibrium, a brief moment where the shield finally felt as robust as the sword it was designed to parry. The dawn of the true quantum age did not arrive with the thunder of an explosion or the fanfare of a global announcement, but rather as a gradual, crystalline clarity that began to settle over the mechanics of the natural world. It was a phased transition where the chaotic noise of the classical era was slowly filtered through the precise, probabilistic sieves of the fault-tolerant processors that Elias and his colleagues had labored to perfect through decades of iterative frustration. As the first decade of the post-supremacy era unfolded, the geopolitical map had been redrawn not by the movement of borders, but by the depth of a nation's entanglement entropy and its capacity to maintain what was now known as a quantum shield. It was a state of informational sovereignty, where communications were secured by the fundamental laws of physics, rather than the temporary hardness of a mathematical puzzle that could eventually be unraveled by a larger machine. This new Cold War, which many had feared would end in a catastrophic collapse of the global financial system, had instead transformed into a conflict of simulation. The ultimate deterrence was no longer the threat of mutual destruction, but the ability to model a rival's entire industrial and military ecology with such perfect fidelity that any aggressive action could be anticipated, analyzed, and neutralized before its first command was even transmitted through the secure, lattice-based nodes of the global backbone. If you reached the end, thank you for your time. If you'd like to support this style, a like and a subscribe makes a bigger difference than you'd think. Elias stood by the observation window of the facility's upper tier, looking out over the landscape where the shimmering heat haze of the desert seemed to mimic the fluctuating wave functions he spent his days manipulating in the subterranean labs. He realized that the encryption Armageddon they had so feared had been averted not through a single act of heroism, but through the patient, global implementation of post-quantum standards and the birth of a decentralized, quantum-safe internet that rendered the old store now, decrypt later caches into useless digital fossils. The world had split into a new kind of duality, not of East and West, but of those who possessed the computational depth to simulate the complex interplay of molecular bonds, and those who remained tethered to the approximations of the classical past. It was a divide that was being bridged by a new internationalism born of necessity, as the climate crisis demanded the level of material engineering that only quantum simulation could provide. This quantum utility era saw the same machines that could have dismantled the world's secrets redirected toward the immense task of planetary restoration. They solved the Haber-Bosch problem to produce fertilizer with a fraction of the energy previously required, and finally mapped the high-temperature superconductivity that allowed for a global, lossless power grid that could carry the output of fusion reactors across continents without the dissipation that had plagued the copper and silicon era. In the silence of the now-refined cryogenic chambers, the qubits were no longer fragile curiosities, but the architects of a new material reality. They utilized the braiding of non-abelian enneads, topological qubits that held their information in the global geometry of their paths rather than the local state of a particle, to provide a level of stability that had once seemed like a mathematical fantasy. This transition represented the fulfillment of Richard Feynman's original 1982 vision, the realization that to simulate nature, one must build a machine that is itself quantum mechanical. In doing so, humanity had finally moved past the era of digital shadows and into a direct, computational engagement with the fabric of the universe itself at its most fundamental level of probability and phase. The ethical tightrope they had walked for years had led to a plateau where the transparency forced by quantum decryption was balanced by the absolute privacy of quantum key distribution, creating a society where the integrity of information was as much a natural law as gravity. The concept of a secret had evolved from a locked box into a state of shared entanglement that could not be observed without being changed. Elias watched the sunset, the orange light reflecting off the cooling towers of the nearby fusion plant, a facility whose plasma stability was maintained by real-time quantum controllers that predicted and suppressed instabilities at the nanosecond scale. He felt a profound, meditative peace in the knowledge that the digital apocalypse had been a doorway rather than a wall, a transition that had forced humanity to outgrow its reliance on the fragile certainties of the binary age. The archived data in the distant vaults of forgotten intelligence agencies, once a looming threat of retrospective exposure, had been largely rendered irrelevant by the sheer speed of the material and societal revolutions that followed. The secrets of the 20th century became historical curiosities in a world that could now see the energetic landscape of a single protein with the same clarity as a star in the night sky. This new era of global power was characterized by a profound sense of stewardship, where the nation with the most advanced quantum sensors was tasked with monitoring the health of the oceans and the atmosphere with infinitesimal precision. The tools of the silent war became the instruments of a global peace that was as robust as the mathematical lattices that now protected the world's data. As the monitors in the lab pulsed with the rhythmic signatures of error-corrected topological qubits, Elias understood that the code they had cracked was not just a cryptographic one, but the very syntax of reality. It was a language that allowed them to write a more stable and transparent chapter in the history of the human species. The transition was complete. The classical world had become a subset of the quantum, and as the lights of the facility dimmed for the night, the silence that remained was the quiet of a world that had finally learned to speak the language of the universe in its most fundamental and enduring form. The era of the Silent War had passed, leaving behind a world that was no longer afraid of the dark. The transition from the noisy intermediate-scale quantum era to the threshold of true fault tolerance was a period of excruciatingly slow progress, measured not in the grand leaps of public announcements, but in the incremental suppression of 2-qubit gate errors and the painstaking refinement of the surface code's logical lattice. Elias remembered the mid-2020s as a time of profound technical claustrophobia, where the ambition of Shor's algorithm was constantly stifled by the fragility of the superconducting transmon qubits, which would lose their quantum information, their coherence, at the slightest touch of a stray thermal photon or the subtle magnetic flux of a passing elevator. To combat this, the engineering teams had moved beyond simple physical qubits to the implementation of logical qubits, which were essentially virtual entities distributed across a two-dimensional grid of physical processors, using the principle of parity checks to detect and correct errors without actually measuring the sensitive data held in superposition. Before we move on, if you like learning this way, you can quietly hit subscribe so you don't lose this channel later. This process, governed by the stabilizer formalism, required a staggering overhead. To create a single logical qubit with an error rate low enough for complex cryptanalysis, one might need a 1,000-strong array of physical qubits working in perfect, synchronized harmony, a requirement that pushed the limits of the dilution refrigerator's cooling capacity and the bandwidth of the microwave control electronics. Inside the facility, the infrastructure of the golden chandelier had grown into a sprawling complex of coaxial cables and cryo-CMOS controllers, a dense jungle of high-frequency wiring that translated the abstract logic of the quantum algorithms into precisely timed pulses of radiation. These pulses, often lasting only tens of nanoseconds, were calibrated to perform rotations in the Hilbert space with a precision that bordered on the miraculous. Yet the noise remained an ever-present adversary, a statistical shadow that threatened to collapse the entire calculation into a heap of random bits. Elias spent months analyzing the syndrome measurements, the diagnostic data produced by the surface code, looking for the signature strings of errors that indicated a localized failure in the lattice, a process that felt like tracking the movement of ghosts through a lightless cathedral. The sheer complexity of the error correction meant that the computer was spending 99% of its effort simply existing, fighting the second law of thermodynamics just to maintain the integrity of a few dozen logical bits, a state of affairs that critics often cited as proof that a cryptographically relevant machine was a physical impossibility. Yet the threshold theorem provided a mathematical beacon of hope. If the error rate of the individual physical components could be driven below a specific, infinitesimal value, then the logical error rate could be suppressed exponentially by adding more physical qubits to the code. This was the scaling wall, a barrier composed of material science, microwave engineering, and the fundamental limits of signal-to-noise ratios, and crossing it required a transition to new materials like tantalum and the development of qubits with intrinsically higher coherence times. As Elias stood amidst the low-frequency drone of the pulse tube coolers, he contemplated the quantum volume metric, a holistic measure of a system's capability that accounted for both the number of qubits and the depth of the circuits they could execute before falling into decoherence. It was the true measure of progress in the Silent War, a yardstick that tracked the closing distance between current capabilities and the point where the RSA walls would finally crumble. This was the era of the deep transition, where the focus shifted from flashy demonstrations of supremacy to the grueling work of reliability, a period characterized by a meditative focus on the microscopic, the purity of a sapphire substrate, the precision of a Josephson Junction's aluminum oxide barrier, and the mathematical elegance of a fault-tolerant T-gate. The realization of these gates, which were the hardest operations to perform in a protected way, became the obsession of the laboratory, as they were the final piece of the puzzle required to execute a universal set of quantum operations. Elias often found himself looking at the bit flip and phase flip rates as if they were the vital signs of a living organism, a delicate biorhythmic pulse that needed to be shielded from the chaotic, high-temperature world outside. The silence of the lab during this period was not one of inactivity, but of a hyper-focused attention to detail, where a single stray cosmic ray could disrupt a week of calculation, leading to the installation of massive lead shields and deep underground laboratories that mirrored the isolation of neutrino detectors. This environment fostered a unique psychological state among the researchers, a sense of being part of a generational effort that transcended the immediate cycles of the tech industry, a slow-motion revolution that was quietly dismantling the foundations of classical security, one parity check at a time. The transition was a testament to the human capacity for abstraction, as the team learned to manipulate information that they could never directly observe, steering the evolution of wave functions through a landscape of probability that was as real to them as the steel and gold of the machines themselves. As the fidelity finally nudged past the critical threshold, a subtle shift occurred in the atmosphere of the facility. The dread of the encryption Armageddon began to be eclipsed by the sheer wonder of the computational landscape that was opening up, a world where the noise was finally quieted enough to hear the true, coherent voice of the quantum realm. The shift from the frantic fortification of the digital world to the expansive horizon of what Elias began to call the era of quantum utility was marked by a profound change in the sensory experience of the laboratory. The screens once filled with cryptographic vulnerability assessments were now illuminated by the swirling, complex geometries of molecular orbitals and the vibrant heat maps of electron density. No longer tethered exclusively to the destructive potential of Shor's algorithm, the fault-tolerant processors were being tasked with the simulation of the Phi-MoCo cluster. Before we go deeper, if this calm pace feels good, consider subscribing so more chill science waits for you when you need it. The Phi-MoCo cluster was the intricate iron-molybdenum-sulfur core of the nitrogenase enzyme that had for billions of years facilitated the fixation of atmospheric nitrogen at ambient temperatures. Humanity had only ever managed to replicate that process through the brutal, energy-intensive pressures of the Haber-Bosch process. Elias watched the real-time visualization of the quantum dynamics, observing how the machine could perfectly capture the many-body correlations and entanglement within the cluster. It was a task that would have required a classical computer larger than the known universe to calculate with such fidelity. This was the moment where the hardness of the physical world began to soften. The fundamental chemical reactions that underpinned the survival of the species were finally becoming transparent to human engineering. It promised a future where fertilizer production no longer accounted for 3% of the world's carbon emissions. The air in the facility felt charged with a different kind of electricity, a constructive tension that arose from the realization that the same nonlinear logic that could break a nation's secrets could also unlock the secrets of room-temperature superconductivity. That breakthrough was currently being pursued through the systematic simulation of cuprate and nickelate structures within the quantum processor's Hilbert space. Elias spent his evenings tracing the simulated flux lines of Cooper pairs moving through these new, theoretically optimized lattices. He realized that a world without electrical resistance would mean a planetary energy grid of such efficiency that the very concept of an energy crisis would be relegated to the history books alongside the blackouts of the 20th century. This transition was not merely a technological upgrade, but a philosophical pivot. The scientific community moved from the era of observational science to constructive simulation. The properties of new materials were engineered from the bottom up at the quantum level before a single atom was ever manipulated in a physical vat. Carbon-negative polymers, high-capacity solid-state batteries, and catalysts that could scrub CO2 directly from the troposphere were now designed in simulation first. The meditative stillness of the lab was now punctuated by the arrival of material scientists and climate ecologists. Their presence was a testament to the fact that the quantum threshold had been crossed not just for the sake of power or security, but for the sake of survival in an age of ecological instability. Elias felt a profound sense of relief as the golden chandelier became an instrument of planetary restoration. Its golden plates and cryogenic lines served as the forge for a new class of metal-organic frameworks that could selectively trap greenhouse gases with a precision that was previously indistinguishable from magic. This realization that the complexity of the natural world was not a barrier but a language that could finally be spoken transformed the anxiety of the Encryption Armageddon into a quiet, focused optimism. It was a sense that the species had finally acquired the resolution of sight necessary to navigate the intricate thermodynamic landscape of the Earth. The silence of the machines was no longer a harbinger of a looming collapse, but the sound of a silent revolution in chemistry and physics. It was a slow-motion flowering of capability that promised to heal the fractures of the industrial age through the precise application of quantum logic. As Elias monitored the successful simulation of a new catalyst for water splitting, he understood that the true legacy of the quantum race would not be the secrets that were exposed, but the solutions that were finally made possible by the ability to calculate as nature calculates. The transition was a bridge to a post-scarcity reality. It was a journey through the heart of the atom that led back to a world where the constraints of the material were no longer an insurmountable wall, but a series of puzzles to be solved with the quiet, persistent grace of coherent wave functions. Elias adjusted the parameters of the simulation, his hands steady on the interface as the golden heart of the machine continued its cold, perfect dance, weaving the future of the planet one entangled state at a time. In the profound, velvet darkness of the control room, the holographic interfaces cast a soft, cerulean glow over Dr. Elias Thorne's features, illuminating the lines of a face that had aged alongside the technology he once feared would dismantle the world. The transition was now absolute, a quiet hegemony of the coherent state that had permeated every level of human infrastructure, from the planetary energy grid to the delicate, synaptic interfaces used in modern neurology. As Elias watched the global coherence monitors, he realized that the silent war for quantum supremacy had not ended with a victor's parade, but with a universal realization of the observer's role in the fabric of reality, a shift that had transformed the geopolitical landscape into one of mutual transparency and verified equilibrium. If you reached the end, thank you for your time. If you'd like to support this style, a like and a subscribe makes a bigger difference than you'd think. The same quantum sensors that could detect the infinitesimal magnetic signatures of a submarine miles beneath the Arctic ice were now being used to map the human brain with single neuron resolution, revealing a world where the macroscopic functions of consciousness seemed to dance on the edge of the same quantum effects that powered the golden chandeliers in his lab. This was the final frontier of the quantum revolution. The understanding that biology itself had been utilizing the principles of entanglement and superposition for eons, from the light harvesting efficiency of photosynthetic complexes to the navigational sensitivity of migratory birds. And now, finally, the human mind was beginning to interface directly with this probabilistic logic. The urgency of the Encryption Armageddon felt like a distant, archaic memory, a relic of a time when the world believed that a secret could be kept behind the walls of a mathematical puzzle. In this new era, privacy was no longer a function of hardness, but a property of the vacuum itself, protected by the no-cloning theorem and the inherent fragility of the unmeasured state. Elias adjusted the sensitivity of a local sensor array, observing the rhythmic, non-local correlations of a citywide quantum key network, and he felt a deep, meditative satisfaction in the knowledge that the technological earthquake had not shattered civilization, but had instead provided it with a more resilient foundation. The global power dynamics had settled into a quantum peace, where the ability to simulate any physical system meant that the traditional incentives for industrial espionage and resource-based conflict had been superseded by a collective effort to manage the thermodynamics of a cooling planet. This was a world of optimal design, where the scarcity of the classical age was being systematically disassembled by the abundance of the quantum simulation, creating a society that functioned more like a coherent wave function than a collection of discrete, colliding particles. The silence of the laboratory, once filled with the tension of a looming catastrophe, was now the silence of a library where the books were written in the language of the universe, and for the first time, humanity was reading the text without the distortion of classical approximations. Elias stood up, his joints protesting with the gentle stiffness of age, and walked to the window to see the lights of the megalopolis below, a city powered by the sun and secured by the lattice, where every transaction and every communication was a testament to the stability of the high-dimensional geometry they had pioneered. The transition from the digital age to the quantum era was complete, leaving behind a world where the quietude of the laboratory had become the fundamental rhythm of a more transparent and enduring human history.